Okay. Hello, everybody. Sorry for the delay. My name is Vince Vitro. I'm a computational scientist at Mix. He was in computational fluid dynamics and computational engineering. So I'm here a little bit with you guys about how to use HPC in engineering. I'm obviously not going to hit every possible use, but I'm going to try to give you a fairly broad spectrum of some of the different sorts of things that we can do computationally in engineering sense, and why very often to do that all or to scale them up, it requires high-performance computing. So talk a little bit about why do we get what problems we're interested in solving using HPC and computational resources. We're going to look at some very specific stuff that is very prevalent in engineering, which is using PDEs to do solutions of linear systems. Say PDEs give us the large linear systems, and we use high-performance computing to solve those. Heard a little bit about why it's necessary to use HPC sometimes, and discuss some commonly used HPC codes. So I would like to thank the UT Chattanooga Sim Center for a great number of the graphics and videos here. Excellent source of visual materials, and I really appreciate what they've done. We as engineers use simulation. There are lots and lots of good reasons. Is that it is expensive to build and test things. And the more complicated the actual machinery or device or layout or whatever you have, depends on the situation. Are you dealing with a whole city? Are you dealing with a very small, very expensive part? You don't want to necessarily have to break it and try it again, break it, remanufacture it every single time. It's very expensive very quickly. And so we can determine a basic viability about a product, ensure that it's actually going to be performing close to what we would expect. We want to test computationally before we go into the field. Avoid destructive testing on things such as, if I give you, for instance, one of the things we're going to discuss in here is disaster mitigation software. Obviously, nobody's going to volunteer their city and be like, hey, yeah, you can drop a bomb and we'll just see how we react. Right? No, that's bad news. So, consequence, what we often try to do is try to mimic those things in computational simulation. Do that, but obviously it's not an exact replica. But we'll look at trends. We're able to look at mitigation strategies based on those trends. And one of the other things that we have to deal with in engineering often is we want to optimize the design. We want to take something that currently exists. What we'll do is to make it better. I'll give you an instance of, for instance, a wing. We want to make that wing have optimal lift, minimize, maximize lift. We can look at things like the adjoint, which is kind of an add-on to the normal PDE solution method for those equations, and use adjoint in other respects too. This method would allow us to do optimization. So, examples of engineering problems. Number one, Microsoft Office. Sorry, your show. Again, what are some things that we can do? I'm going to for the move. We'll do that. Right. We'll do that. You guys can see it, but they can't. I apologize. Do and I'm thinking that one. Every time I'm going to open this PowerPoint, it's got video, and the videos are WMVs, and PowerPoint tends to count. So what I'm going to do is we're going to go a little different route here. All of you all that are having to watch me play around with this, it won't necessarily be better on your machine because we're just going to be looking at this. So I'm going to open it up as a PDF. And we'll look at the video. Okay, so as we were saying before all that went awry, other things that we want to be able to deal with. One class of engineering problems that we want to look at is discrete event simulation. Okay? For instance, you may want to model human behavior in terms of traffic and evacuation. Okay? How do we do that? Well, there's not necessarily a PDE that presents human behavior perfectly. Okay? We've done traffic problems with PDEs. There are indeed PDEs that model traffic flow fairly well. When you have something like a disaster, a lot of times those break down. People don't follow their normal patterns. People do all kinds of crazy things. So look at it, things like agent-based models, where you effectively have, how many of these agents, each agent has a specific place of residence, a route that they take home, they have a certain number of kids, they work in a certain place. They have all these different facets about them that are actually as part of that class object that Java C will have. And then, based on all those objects move around. And when we run another object, they're set up to react in a certain way. This is on a PDE. This is based purely on sort of a statistical approach. What that means, more agents, the more accurate your approach, correct? So as a consequence, if you want to have lots and lots and lots of these agents, and let's say agent takes 100 space, and you want to have billions of agents, you're suddenly well outside of the ability to compute this on a regular computing platform. You need to be able to take it, discretize it, and put it into maybe a high-performance computing platform. So here's what I mean when I say this city, what we have here is we have a contaminant release. Over top model, okay? The model on the top is actually a model of plume, the release. And we're using basically like atmospheric boundary layer. We're taking this idea of turbulence modeling, which used to be on a boundary, say, against the wings. We're talking about micro scale. And we have it at a macro scale concept. It's really not macro scale if you're looking at the boundary layers being the entire surface of the Earth. Okay? So basically scaling up the ideas that we have about turbulence modeling and about forking and all these things that exist on a very minute microscopic level, and we're looking at them in a macroscopic fashion. We figure out, based on wind and different other environmental conditions, where that plume is going to go. Right? Obviously, it's a situation where you don't want to be like, okay, the wind's out of the east today, drop a bomb. See what happens. All right. This is a situation where you need to be able to test several different configurations in advance. Simulation is the best way to do that. Now, we want to and pair it with some of the agent-based models. Okay? And agents, as you can see here, and I'm going to show you the movie in just a moment. This agent modeling, let me use slide back. All right. Let this stay here. Okay, so if you look, as you can, each of these little dots you can see moving about are agents, right? They each have several different characteristics attached to them. Again, where are they going? Are they coming into or out of the city, depending on the time of day? They may be going to work, they may be leaving work, they may be picking up their kids at school. And what we're able to do is we're able to determine, given a situation such as a plume, whether it be a chemical situation or an actual weapon, Okay? Scenario, what are we trying to do? Well, we're trying to figure out with some basic boundary conditions. It happens here at this time, and we tell people to shelter in place, we tell them to try to evacuate. What happens? And what you see, as very quickly is becoming obvious, is all those little blue dots are kind of stagnant. What you see is it's very difficult for people to get out. In fact, at a certain point, with no mitigation strategy, you have gridlock. And what they do is go into this very model and goes off a road, or perhaps put a traffic light out of service, or say, well, you know, based on this, it looks like these folks are in the clear. They need to shelter in place so that these other folks can get out. That's decision making. That's the kind of mitigation strategy determined you can do with these sorts of agent-based models. This is an interesting area in engineering that's fairly new. Agent-based models aren't particularly new, but using them in this sense is new. And part of the reason for that is because it previously was prohibited to get enough agents on a system to get a reasonable simulation. Now, one of the things that makes that possible is high-performance computing. Right? We can take the city and divide it up into, say, 4, 5, 6, 100 sections, and form one of those off to a separate machine. Periodically, they talk to each other and say, hey, the people over there, what do they do? The people in your processor, what do they do? And then they communicate, update, and move on. All right. Like I said, we'll deal with the issue later, and I apologize again for y'all having to watch that. All right. Now here's some more examples. All right, so like a fluid flow using Navier-Stokes. Navier-Stokes is a system of equations that describes fluid flow, and fluid meaning air, water, sometimes even all sorts of things. We have several different degrees of exactness. Okay? In this particular example, to simplify the equation set I'm going to show you, I'm going to discuss equations. Order equations are essentially the Navier-Stokes equations where we assume some things away. For instance, there's no viscosity. That seems like a very trivial thing. Why would you get rid of that? What's fine is when you have to deal with viscosity, you have to deal with the wall, you end up with turbulence, eddies, and all these other things you don't necessarily want to deal with in a base. Okay? Now, I'm talking about the 2D version here again for simplicity of trying to kind of make a point. But it is interesting to be aware that even in 2D, your matrix you have to solve this PDE is n squared, where n is the number of nodes in your discretized environment. Okay? If you're in 3D, it becomes n cubed. So what we really have to do is we have to be cognizant that these problems are very computation intensive, and to do things that are even remotely real world, we need more than a desktop. Right, so things that we can do with this. Well, we can look at, here's an F16XL, something I worked on in graduate school. And what we're looking at how these pivot boards are used for. Right? So what we can do is instead of actually having to spend the money, jet, put it up in the air, and have to do all these different test runs, different mock numbers, right? We can test those on a computer. When we test those on a computer, it's not free, but it's significantly cheap. Okay? And we also don't take the chance that, the plane falls off the sky and someone dies. So we can look at something about pollution in the Smoky Mountains. We live here in UP. Knoxville, we're right here in the Smoky Mountains. Most visited national park, also the most polluted. And the reason that is twofold. One, lots of visitors, lots of cars, lots of pollution. Certainly, there's a reason these things are called the Smoky Mountains to begin with. They love these little temperatures, which is where we get the fog from. And of course, you combine that with carbon monoxide, you get smog. We want to look at where were some of the hot spots for this smog. Namely, we could say, if I'm going to build a retirement to people with smoke, I probably don't want to put it somewhere it's going to be kind of smog. Because then folks with asthma or other breathing ailments die because they move to the smoky. We don't want that. Usually we can solve that. this video for the moment since we're running a little short on time and we have some issues with the video. Don't worry, it's not a math lesson. I show you this because I want you to be cognizant of what's occurring most of the time when you see people solving partial differential equations using HPC. They solve the partial differential equation often in integral form. And see here, okay, you have the partial differential equation and you have the Q values. Q's are flow state variables. Okay, I can determine things about density, velocity, energy. All right, what I'm looking to do here is there's a million ways you can formulate, but the most common way you'll see with fluid dynamics is what we call the control volume law. We're not talking about a control volume. Looking at a fluid, we have a fixed frame of reference, and we consider the fluid's behavior on the way in and on the way out. Okay? So we're not constantly trying to move our frame of reference. We stick in one spot and we look at how the fluid goes through that control volume. Okay? So what I'm interested in is fluxes. Fluxes go into these control volumes, fluxes going out. This is how we're able to solve these equations in a conservative form. So some of you that haven't necessarily worked with the metric format, you go, okay, that's all well and good, but tell me a little bit about these nodes. Tell me a little bit about these points, information. Okay? So we're trying to do a flow solution. This is a 2D example. Okay? This is the side view of an airfoil. All right? That's if you were looking at an airplane flying in this way, and I was looking at it perpendicular to the airplane, looking down the wing. Okay? You see here all these different nodes. All those nodes are going to have values. Okay? And they're going to be initialized either as free stream values, or they're going to be initialized as no slip right along the wall, because as we all know, viscosity says that when a fluid hits a wall of solid surface, it stops. Okay? It's simplified, we'll go with it. Take this particular mesh, which is a distribution of points based on what we think the most interesting physics phenomena are. All these little nodes, we create control volumes around. Okay, so right here, we have the central node. We have this median dual meaning it just goes through the midpoints of all the sides. Okay? This is our control volume. We're interested in flux into and out of this control volume. Once we have mesh, we have that equation that we're interested in solving. We've got our flow field initialized and all that good stuff. What we can do is using Green's theorem. All right, by the way, this is Green's theorem for reconstructing the gradient. And we use Taylor series expansion to take our initial system and we're like this. Now, a whole semester's worth of why in the world you want to make it look like this. Okay? If I say, the reason we do this is because we want to be able to solve this system of equations and it has to be linear. All these equations are inherently nonlinear. All right? What does that mean? Well, nonlinear means that they often have variables that depend on a variable. So you have things that is changing with respect to velocity and time, but velocity is also changing with respect to time. Okay, that's a nonlinear situation. And so when we linearize it, we come up with this form. Now that we have linearized form, we've got a system of equations, okay? This is a huge system of equations. Now, what we have here is we effectively have node 0. How are they? Node 1 is 0. Node 2 is 0. So on and so on and so forth, okay? Not connects to every other node. As a consequence, we have a sparse matrix, okay? What's that? These are zeros. The vast majority, or some small majority. All right? In that particular situation, you still have this huge sparse matrix solve, and you have a bunch of different ways you can handle that. Okay. One is that you can sit there on your desktop and you can say, well, I only can fit this many elements of memory, and so this is as big as my system. Another option You use some rest row storage to try to shrink that memory pool. Some sort of laws or LAPACK call or to solve a sparse matrix. But then you have to sort of store them. Because there are formats in order to store these sorts of matrices without taking up that much room. He said that. These huge matrices, okay? If we're talking about a case where I'm looking at, say, a jet 3D supersonic, I forget that. It's about the plume. I created that grid with my software back in the day. They had about 1 billion elements. Okay? So 1 billion elements, each of those 1 billion elements has, well, in that is 1, 2, 3, 4, 5 variables. Okay? So each of those is a double. That's 8 bytes. So 8 times 5 is 40, times 1 billion is 40 billion. That's 40 gigabytes. Okay? That's bigger than most people's RAM memory. Way bigger. Okay? And that's just to store state variables. Forget storing immediate chunks of the equation to solve. You have to like this and discretize them out over many different processors. Take your discretization and you say, okay, you are on processing element 0, you are on 1, you are on 2. Then you do MPI communication to update the boundary step. The point is something that is a reasonably real engineering problem that you want to get even close to physically accurate result. You can't on a top. You can't. You can try COMSOL. You can try some of these other things. I give, for instance, some of these commercial software packages take 0 to be 10 to the negative third. 0.01. That is 0. in a sense of turbulence model, that could be a very relevant number. Okay. Some turbulence model, you need to look at 0 being 10 to the negative 12. So the reason that they cut off so early is that they don't have the room. HPC comes. HPC has the room. All right. So in the first slides, I want to talk about a couple of problems that not only this is how to test them, we've discussed that, but why. Okay. These two specific problems here. One is an emergency propeller reversal, and is one of these jets, Osprey aircraft. Okay. Both of these, they designed these, they built them, they tested them. They're service, and both of them ran into a small issue. Okay, the particular propeller ran into some serious cavitation issues. Right? Remember, cavitation occurs when you have this sort of cracked back vortices forming, in which you have a bunch of little air bubbles that have high pressure. And they bam right up against that metal and start creating pock marks. Little by little, deteriorates the metal, and you lose your prop. And if you're in a marine and you lose your prop, you are now a shipwreck. Okay? So, what do you? Well, if you run a computer simulation, you can run a computer simulation of this at different RPM, even when you could test. Obviously, you'd be like, well, there's like 100 million different options. An hour from a wind tunnel or a water tunnel is not cheap. So you more options, and tested more options. They were able to determine that at a specific speed, that cavitation was going to occur based on the design. Period. And so the goal was to never ever run at that speed for any significant amount of time. It runs up right through that speed. So just as you begin to have those cavitation effects, you pass speed by, and the flow profile changes. More specific, they right? If the aircraft, just like a rubber prop aircraft, but the prop can flip up and it can take off straight down like a helicopter. Okay? So cool, everybody was excited, and they took this, put it in production, and put a bunch of Marines on it, sent it up, and came crashing down here with it. It's terrible. Okay. They couldn't figure it out. Again, it wasn't like they just built this in their backyard, thrown some people in, and said, "Oh, go on, see what happens." All right. done exhaustive testing on it. They just could not figure out what was happening. It turned out that it is a very specific RPM, in this case 592. It's specific. What happened is you have vortices. One is spinning this way, the other spinning the opposite way. I don't know if I can do that. In that situation, lift goes to 0 and it falls out of the sky. And that they never would have found in testing. But we were able to do this huge gamut of different rush speeds. We were able to determine exactly what was happening. And what did they do about it? That's your next question, right? Well, what they did about it is they said, we're never going to spin at those 2 RPM. All right? Go right through them. In fact, I think what they did, they ended up one of the rotors off, get the other one through that RPM, and then bring them back up to speed. All right. It's not planes, trains, and automobiles that we can mess around with in engineering. Things that we can deal with in engineering is, well, actually, we do pretty much anything that has an equation of the behavior, if it's an imperfect equation. I'll say okay. Here we have those equations for electricity and magnetism. Okay. Why would we care? Well, first of all, we can't really see such, right? Right. You take and you send out RF signals. I can't see them. My phone's doing it right now. Your phone's doing it right now. I can't see anything. Okay. So what we have to do is visualize what's occurring to look at the next generation antenna. What shapes can we make antenna that will actually absorb more of these sorts of electromagnetic waves? We're building military exploits. Fiber reinforced concrete. Working with the gentleman on this recently. They will be able to simulate if you have a building made out of X type of concrete with X type of steel fiber shielding, RF attenuation. Can you keep signals out? RF signals, of course, things that could be used to shut down somebody's power grid or intercept transmissions, several different. Okay? And a very interesting problem right now to the military and many people, this new age of sort of electronic warfare. What do you do to keep these sorts of things safe? You have a data center in the middle of Baghdad. What do you keep it safe from cyber? Okay. Example of electromagnetic scattering, and it says it's an infinite cylinder. Okay. An infinite cylinder just means an antenna, right? So it's a cylinder, but its height is much, much greater than its range. That's how it's an infinite cylinder. Okay. So here I have a movie that, again, I will. This is pretty cool. This is what happens. We were able to use a machine to do exact experiment. A small box, and in that small box, you pass waves through it, and you're able to look at the wavelength, and they were to match experiment with reality. So here, right here, you're looking at the wavelength down to, I believe it was 10 to the negative 6 accuracy. There to determine exactly that these wavelengths would be. They look at it with the machine, the exact same numbers from their simulation. So again, in that machine, I want to say about $100,000 machine. And its code was written by a graduate student that cost $20,000 a year, so it's a little cheaper. Okay. So, optimizing current design. This is one of my favorite little stories about adjoint method optimization, and I'm actually not going to go into the math. Having said, most of you are on the road. You've seen a truck driving down the road. It has these baffles, big long pieces of aluminum, maybe fiberglass. Sometimes they're right underneath the truck. Sometimes they're between the cab and the trailer. Sometimes they're on the back of the trailer. We've all seen them getting very prevalent in years. Well, for those that when you have a truck, it is like, right? It is like some of the worst drag of any vehicle on the road. The problem with that is at the back of the truck, you have that are beginning to come into fruition. you have a low pressure zone in the back of the truck. Now, my understanding, I think I'm pretty right on that, is that if you have something pushing on something and then you have something sucking it backwards, you just do not have drag, right? Maybe not exactly double, depends on how hard the suction is, right? But you're increasing the drag on the truck. If there's more drag on the truck, the motor has to work harder. And if the motor has to work harder, it uses more fuel. And what is the most expensive part of the truck? So even more than the driver. That's enough. Okay? So what do we do? Oh, I'm sorry. Oh, actually, I was about to kick out of there. Intentions, right? So I want to show this pretty cool video. All right, so a model of a truck, and they're fixing some baffles to it. Okay, and after they fix these baffles to it in these several different spots, what they're going to do, they're going to take this geometry, which is generated in CAD, right, and put a mesh around it, and then they're going to run a flow solution. Now, the computer does not spit out these graphics, fortunately. The computer spits out velocity to given data. What we're able to do is we're able to utilize our visualization software, visualization software, and draw those trace lines, those velocity lines. Now, what's happening here is with the baffles on, which is the one on the top, look how much smaller that weight region behind the truck is. That there behind the truck, that weight region being smaller is absolutely crucial. That is what is going to give you drag reduction. How drag reduction? Well, based on this particular profile, in working with a trucking company called US Express, they were able to determine the approximately 8% fuel savings. When they actually all the stuff on the trucks, they found it to be more like 10%. That's not normal. Normally you think it'd be a little less, but actually they underestimated. So 10 fuel savings. Your $15 a month gas bill, that's $5 million a month. That's what Express is looking at. Over the course of 11 months, it's 12.3. Okay. So this is how we in engineering are very interested that we are respectful and responsible with our resources, right? There's more shares. We want to be responsible. And all we can find ways to be responsible with them and not necessarily even penalize them in any way. It's just a matter of optimizing. All right. If you're a chemical engineer, by the way, I should point out, I tried to put in aerospace, mechanical, chemical, civil coming up. I did not put in electrical engineering and computer science because I kind of figured if you're electrical engineering and computer science, you're somewhat aware of it. Okay. That was, a little direct, obvious connection. All right, so here we have a situation where we're looking at a fuel cell, bloom energy. All right, and with this fuel cell, the way the cell works effectively is it takes methane gas, which is a much more abundant and simple form of hydrogen to get a hold of, right, from natural gas. And they go through a anode to cathode, and in doing so, you obtain electricity, and our product is the hydrogen and the oxygen using together to give two water. All right? Right? It's like the cleanest energy you can imagine. If you have hydrogen and oxygen, you add electricity and water. Huge win. Right? Everybody loves that. Why do we use gas? Well, there's no free hydrogen. The hydrogen very easily is, of course, to electrolyze water, which means the electricity start. And working on a system where that will become, where it will be efficient enough that they'll be able to electrolyze water and then run it through to generate significantly more electricity than it took to electrolyze the water. Okay. So, really amazing concept. The problem is, as we all know with most things, the efficiency, right? It is not cost efficient at the moment for the amount of power you use. Now, it's gotten significantly better, still to buy the hardware, but I will say this, the natural gas that they use here is actually, use the natural gas here, they're actually able to get, I believe, 5 times more energy usage out of it than just cool. Why do we care? What do we do with that engine? Great, fuel cell. What do we do with that? The problems is you have fuel cells, these anode and cathode arrays, and you have the inflow and you have the outflow, and in the middle, we hope that things were properly flowing through there, but there's a way of determining if we were at a full saturation. And notice in this first diagram here, without reshaping the channels, okay, notice that there's very little actual activity going on throughout the middle of these channels as far as the electricity goes, okay? You're not getting much airflow up there, so it's like wasted space. At channels, you notice now that the activity increased in between anode cathode, which means efficiency, which means a better product that's more inexpensive to operate and possibly, really make it in the market compared to, say, fossil fuels, like that. Again, that HPC. Why? This particular mesh right here, we were having to do, several million elements to get these specific turbulence models in order to figure out where these engines were formed. Okay? All right. Structural analysis for all you civil engineers out there, right? We want to look at things like glassworthiness of materials and structures, like bonding. Again, here, you actually want to model each member of a large structure, and then actually have some sort of equation set on top of that, look elastic perhaps, chart reactions of all those elements with each other. You can't look at a computer. You have just too many data points. And you get simple models, which is how we're able to determine over the past 20 years that they're all functional. But the advent of HPC, that we've been able to truly discretize these things to a level of reality that we didn't previously have. All right. Here's an example. This is actually from Consol and Solid. Right. They're good at linear elastic stuff. And so what you do is you say a cross or some other part, and you apply forces to that, and then you say solve. It will go in there and it will set up a system of linear elastic equations, and so in order to determine what structure will fail and what sort of factor of safety you have based on that failure. Okay? Now, you're going to do that on a home computer. That's true, you can. If you have a souped up desktop, you can run a tiny little bridge truss you made in your engineering 101 class. Try bridge. And once again, farm out of an HPC environment. All right. I wanted to mention that one of the things that we found is very interesting is road beds. Road beds have a very different sort of elasticity. It's not a linear elasticity. You have the different layers of compaction underneath the road bed. Separate set of equations to model those, and if you want to model even a small city's road, like say Chattanooga, you'll need hundreds of gigabytes of memory to fit that entire system into your model. And what they want to do is they want to simulate different negative effects on these roads, whether it's sinkholes, wetting, earthquakes, mineral decay, to determine what roads to do next. We all know there's not infinite budget for roads. All right. So codes running at NICS. We have lots of different options out there. Two of the best CFD codes that are free and open source, but we see a lot of at NICS, like OpenFOAM and SUT, which is Stanford University Unstructured Code, right? Very popular HPC codes used for engineering. And then a couple of examples here that I worked on, a couple of HPC codes, one called DNS out of Texas A&M, and one called FASTA out of Texas Tech. and several other places, actually. Even these ported over to HPC, you can solve large systems. For instance, something like Reynolds number of 15 million and 150,000 time steps in less than a day. Right? That can get really, really tedious, crunchy. So what we optimize every last little thing we can. Sometimes it's about reading files. Right? Sometimes you have a file and you spread over more different object servers. You can read it. Okay? Others are in a situation where you have memory bandwidth. Often engineering, the data is so significant and interconnected that there's not much embarrassing parallelism, and so you have to be very cognizant of how quickly you're able to move that in and out of memory. Okay? They all use these LPAC and BLAST functions, which are constantly being updated and upgraded here with ICL, University of Tennessee, in order to do architecture accelerators, the newest, best, fastest version of these people. And so that's the beauty of HPC and engineering is math underneath. And as long as they're developing these math kernels, we're going to have faster and faster engineering. Here's droplet laden isotropic turbulence. Okay, here we need 24 to the third, which is a billion data points. Just look at droplets within this one tiny control ball. Okay, I'm going to do a whole airplane. Take space. We can look at things like blood flow. Right, this is blood flow through the lungs. Right, and we wanted to do here is we actually found some embarrassing parallelism, and so we were able to thread the code. And by threading code, we sped it up fast enough to actually be able to do some real problems. So, given that I'm out of time here, I want to make sure there's a few minutes for questions. And thank you very much. Here's my contact. All right. I'm going to pop into this real quick so I can be in SharePoint. Are there any SharePoint questions? Oh, look. I just got typed in questions. Anybody in the room have any questions?